Hello, Brivana, and all the STEM Academy. This is a Mr. Kim for calculus rotating about an axis. You guys are actually entering the later portions of calculus, where this is probably entering the bit of calculus 2 in a way. It is challenging, but at the same time, it's really not that bad because when you're rotating about an axis, I always want you to think of circles. And when you're given a radius of a circle, you can always find the area, and when you integrate that, it becomes a volume, and that's basically what you're going to do. So let's just jump right in. Okay. So the first question, it says find the volumes, okay, of the solid generated by, I don't know why I can't scroll up here. Okay, generated by revolving the regions by the given lines and the curves about the x-axis. So here, we're talking about finding the volumes of the solids generated by revolving the regions, okay? I know that this part right here, I don't know why this 2 out of 4 is showing, but let's see if I could just get rid of that. Okay. Okay, so I guess I can't get rid of that. So find the volumes of the solids generated by the revolving the regions bounded by the lines and the curves of the x-axis. So it's really good for you in the very first place to have some sort of a visual for what's going to happen. So let's translate this. So on an xy coordinate plane here, we have x is equal to 2, y is equal to 0. So I hope that those are going to be easy. So y is equal to 0 means it's simply going to be a horizontal line down this way. X is going to be equal to 2 means it's going to be this, okay, where you're just going to draw a straight vertical line. And then y equals x squared is when you have a parabola shape. So when x is 1, y is 1, and x is 2, y is 4. So you have this, basically this curve that's going to go all the way also in the opposite direction. We call this parabola, right? So just find the volumes of the solid generated by revolving the regions bounded by the lines and the curves about the x-axis. So what that means is you're really focusing on this shape right here. Okay, this is the x-axis, this is the line, and this is the curve. So the area that's bounded by this, it's basically this sort of like a triangle looking thing, but it's really not. It's basically a shape that looks like that. Okay? Now, we're talking about rotating this about the x-axis. So what that's going to mean is that this shape right here, okay? For some reason I can't really zoom in. Okay? All right. So this shape right here, it's going to rotate about the x-axis. So this shape will look something like this. Like it's gonna be like a kind of like a circus, one of those tents, like a little 90 degrees rotated. Because what's gonna happen is that this shape, this triangular shape, is gonna rotate about this x-axis, in which it's going to create this 3D shape model, right? So in order for us to really see that in more in detail, we need to know the formula for this. We are going to integrate, okay? We gotta integrate in terms of the x direction, so it's gonna be dx. Why are we integrating in terms of dx? Well, it's because it starts from here and it ends up here, and that is going to be my boundaries, right? Well, you can also think of it in terms of doing it in terms of dy as well, but then it's going to be a little bit more complicated to do so. So first of all, what I want to do is in terms of x, how much do I go? What is going to be in boundaries? It starts at 0, and this is at 2, right? So that's the boundary. So my integration starts from 0 to 2. Okay? And if you remember, this, if you were to rotate, all of these lines is what we call the radius of this one circle. Even the circle here, that's the radius. Even for a circle here, that's the radius. So we have basically different circles at different x values. So we want to integrate at that particular location in terms of x. But what function are we going to integrate? It's going to be the very first curve that it's given to us as y equals x squared. So what essentially happens is that we are integrating from 0 to 2, and the radius here, okay, oh, come on, I can't really zoom in. The radius here, for example, let's say I give you this, okay, that's your radius, okay, in purple. The highest value here that the radius, well, you can pretty much tell that's 1, 2, 3, 4, right? That the radius is 4. But another way to think of it is that whatever this value is, okay, every single point here it has a corresponding y value or f of x value at different location. And we want to make sure that we find just from here to this value here, right? So for example, from here to here, that's a radius. From here to here, that's a radius. From here to here, that's the radius, right? So how do we find out each of these different values? So because the radius is not always 4. Just this is 4, the very last one, but not this one, right? So how do we represent radius? The representation of the radius is as follows. You gotta take the value of x squared at those different locations, and you need to subtract away this bottom one. What is this bottom value? Is the y is equal to 0 and y is equal to x squared, right? In other words, you want to take the top curve minus the bottom curve. So what is x squared minus 0? It's just x squared. Because when x is 2, y is 4. When x is 1, y is 1. So actually the radius value actually becomes x squared, believe it or not. So if we are to integrate the pi r squared, because that's the area of circle, I hope you remember that. If I integrate the area of the circle shape that's given to us, then we find the volume of the shape, in which it looks something like this. That's like a Hershey Kiss volume shape. That's what's going to look like. And we want to integrate in terms of dx, so change in x, because we're shifting from 0 to 2. That's the change in x in which what we're going to be dealing with. When you're given these the integration, you always want to take out the pi out. So volume is pi 0 to 2 radius squared times dx. But what is the radius again? The radius we established was x squared, right? So I'm going to use red here. Volume is pi is outside, integrating 0 to 2 from x squared dx. So when we do the volume, pi integration from 0 to 2, this is going to actually become x to the 4th power. So how do we integrate x to the 4th power? Now if you remember the power rule, if we're kind of going back, remember that we're going to add the 1, so it becomes x to the 5th, but we want to make sure that the fraction comes into the front, in which when we differentiate it, when we take the derivative of it, it goes back to the x to the 4th power, right? So it becomes 1/5. Because if I were to derive x to the 5th, power rule means that I'm going to multiply 5 by 1/5, in which they will cancel each other out. And then you're going to have to subtract 1 from the exponent, so it becomes x to the 4th, which is the original function. Then don't forget your integration, always leave it at plus c at the end. Okay? So, and then I want to do that from 0 to 2. Remember, the pi is still out in the very beginning outside of it. So my final answer here is pi times 1/5 2 squared, 2 to the 5th plus c, minus, because that is the very first portion when you plug that in, 1/5 times 0 to the 5th power plus c. But I hope you realize that when you do that, the c, it actually doesn't matter whatsoever, because they will cancel each other out by this minus sign. And 0 times 1/5, and 0 raised to the 5th times 1/5 is just 0, so I don't even have to worry about that. So really my final answer really just becomes pi times 1/5 2 to the 5th power. That's 32 over 5 times pi. And that is going to be the volume of this Hershey Kiss looking pyramid shape, or cone shape basically. Okay, all right, so hope this question helped. I can't zoom out again. You can't see it, but I'm trying to keep on zooming out. Okay, so hopefully that does the trick. Good. All right, so let's move on to the next question here. This is being very weird. Okay, there we go. All right, so y is equal to square root of cosine of x. And we're given the boundary 0 to pi over 2. Thank God for that. And then y equals 0 and x equal to 0. So we want to find out where is this rotating at. This question here, it said that generated about the x-axis, right? So we're rotating. You're rotating about x-axis again when we're finding the boundaries between these three graphs and this given domain. Okay, so let's draw the shape. I want to always have a visual for myself. Remember in Algebra 2 class, we took it last year, what happens when you plug in x as 0 and excess pi over 2 for cosine of x. Let's go over the basics. Well, for cosine of x, it became 1. And for when it was pi over 2, it was at 0. But what happens when you were to simply take the square root of cosine of x value? Well, for 0, it's simply going to still end up being at 1. And at pi over 2, it's still going to end up being at 0, right? Maybe I should just erase this just for clarification. But all the values in the middle of these two guys, well, they'll be square rooted from whatever this value is. But I don't really care because that's the final end product. So at 0 and at 0 and at 1, those are your x value, and those could be the coordinates, and it's going to go on and on and on. At 0, I'm going to end up at 1. And at 1, I'm going to end up at 0. That still does not change. So you're going to have what we call somewhat of a quarter of a circle kind of looking shape. That does not change. And then it says it's boundaried by x equal to 0, which is this horizontal. X equal to 0 is this vertical line. And y is equal to 0 means this horizontal line. So here is what the shape, the 2D shape, is what's going to look like. And imagine if I were to rotate this about an x-axis. What am I going to get? I'm going to get a dome. I'm going to get this like a beanie hat looking thing that looks like a sort of like a dome shape, or like a hemisphere, if you will, with the radius of, what would be my radius? That's the question, right? Well, here, all of my radius, you have to take a look at it from the change in x. So again, let's make an integration from 0 to 1. Because I go from 0 to 1, dx. And it's always pi r squared. It's always going to be a circular shape. Okay? Now again, I need you guys to take a look at this very, very carefully, because my radius is not always going to be, it's going to be just 1. Well, this particular shape right now is 1, but what about at here? What about a circle here? What about a circle here? Remember, they all have different radii for different types of x values. So again, always it's the top curve minus the bottom curve. Top curve minus the bottom curve. The top curve here was that y is equal to square root of cosine of x. The bottom curve here was just that y equals 0, so it makes my math a little bit easier to do. So top curve minus the bottom curve is simply cosine of x square rooted, and that will be your radius, in which you're going to be utilizing here. Okay, so let's plug it in and see what we get. So pi, always bring it outside, integration of 0 to 1. I'm going to draw this, I'm going to write this on a separate sheet of paper. So 0 to 1, pi outside, and then it's going to be square root of cosine of x dx. But remember, it's radius squared, right? Because it's radius, and I'm going to plug it in so I get squared. Which makes my math a lot easier to do, because imagine if I had to take the square root and square it, they just both cancel each other out. So what I'm actually going to do is I'm integrating cosine of x dx from 0 to 1. If you guys remember the trig rule, if the function is a sine of x, derivative of sine of x is cosine of x. If the function is cosine of x, derivative of cosine of x is negative sine of x. This is a trig identity that I always want you to remember. So if I'm integrating, which means I'm starting from here going backwards, integration of cosine of x is simply sine of x, right? Well, sine of x plus c, but remember from the previous question I told you that the c doesn't matter because they cancel each other out anyways. So this is simply saying pi times sine of x, and you're going to plug in from 0 to 1. So it's pi sine of 1, the high x value, minus sine the lower x value. Well, sine of 1, that's simply going to be, that's actually going to be a little bit tricky. Oh, I'm sorry, it's not from 0 to 1, my apologies. Because your x value is from 0 to pi over 2. And then this is to be like, I don't know, pi or something like that. So you have to integrate from 0 to pi over 2. That was my mistake. Sorry about that. So here, you're going to go back, and I'm going to change this to pi over 2. If I was at school, I would have to owe you guys $1 for this, but I'm not at school here. So sine of pi over 2 minus sine of 0. So pi times sine of pi over 2, I believe, if you take a look at your unit circle chart, or if you type that in your calculator, sine of pi over 2, the y value is always your sine value, and your x value is always your cosine value. Hope you remember that. from even Algebra 2 class, and this is 1 comma 0. That's sine of x. So here, this is going to become 1, and this is going to become 0, so it's 1 minus 0, so it's going to be just pi. Pi times 1, essentially. So that's going to be my volume. Okay, so the answer to the second question is pi, and the answer to the first question should be 32 over 5 pi. Okay, hope this video helped with the rotating about an axis. Always remember that the volume is integration of pi r squared dx from x1 to x2. We call that the disk method. Ask your professor about it. I don't know if he's an adjunct professor or not, but that should be the way to go. These two questions are very basic of the volume rotating questions. Once later on, I think your teacher will teach you guys about rotating about a axis, but it's going to be a donut shape. So you have to do the top curve minus the bottom curve and then rotate it. So what we get is sort of like a 3D donut kind of thing. Not just a like a dome or a cone or a those kind of things, but you will always see like a little bit of a circular shape involved with these calculus rotating about an axis. Okay, hope this video helped. Stay safe out there. I'll talk to you guys next time.